Good day and welcome to the Climate Effects and Adaptation in Forests webcast. This webcast is being recorded. At this time, I'd like to turn the webcast to Dr. Ann Marsh. Please go ahead.
Good afternoon, everyone. Welcome to today's webinar. I'm Ann Marsh, Acting Director for Sustainable Forest Management Research at the USDA Forest Service. This webinar is intended to build a better understanding of the scientific foundation of climate change's relationship to working lands and to ensure that climate-informed workforce for USDA, the US government, and important stakeholders. So first, a few housekeeping reminders. Questions for the speakers should be entered in the Q&A box, which is on the lower half of your screen. These questions are only visible to the presenters, the host, and the chat moderator, and we will address as many questions as we can. We encourage you to ask anything that will help you understand the topic. We will respond to as many questions as possible today, and unanswered questions will be used to inform future presentations in this series. This is a science webinar, so our speakers will not be addressing the US government or USDA policies on climate change. Today, we are fortunate to have with us three scientists with extensive expertise on forests, forest management, and their relationship to climate change, and associated disturbances. Our first speaker is Dr. Christopher Fettig, a research entomologist at the Forest Service's Pacific Southwest Research Station. Dr. Fettig's research focuses on forest health and disturbance ecology, with an emphasis on bark beetles, climate change, and wildfire. He has published over 200 research papers and has contributed to and led several important regional and national syntheses and assessments. He currently serves as the federal coordinating lead author for the forest chapter of the 5th National Climate Assessment. Our second speaker is Ms. Maria Janowiak, the Acting Director of the Northern Institute of Applied Climate Science and Acting Director of the USDA Northern Forest Climate Hub. Ms. Janowiak has nearly 15 years of experience in helping natural resource professionals understand and adapt to climate change, with a particular emphasis on systems. She has led multiple vulnerability assessments, created decision support tools, taught courses, and provided direct outreach to thousands of people. She was also recognized with the Climate Adaptation Leadership Award for Natural Resources in 2018. Our final speaker is Dr. Jessica Halofsky, the Director of the USDA Northwest Climate Hub and Forest Service Western Wildland Threat Assessments, which are both housed at Forest Service Pacific Northwest Research Station. In her role, Dr. Halofsky promotes applied climate change science and adaptation in natural resources in the Northwest and across the West. She has a background in forest ecology and fire, but has been doing climate change adaptation work across the West for over a decade. She pioneered one of the first climate change vulnerability assessment and adaptation projects with Olympic National Forest and Park, and since then has co-led 10 other sub-regional to regional scale climate change vulnerability assessment and adaptation partnerships on federal lands around the Western US. Our speakers are going to begin with an overview of how climate change is changing and affecting forests across the US, identifying vulnerabilities for USDA and the public. They will then explore opportunities to proactively address risks to forests and ecosystem services they provide, and also share just a few examples of adaptation strategies and tactics. Please join me in welcoming our speakers. Dr. Fettig, over to you.
Thank you, Ann, for that wonderful introduction. And good morning, or perhaps good afternoon, everyone, depending on where you're participating from. I'm sure most of you are quite aware that much of the Earth's surface has warmed during the late 20th and early 21st century. The figure on the left there that you can see is observed changes in temperature for the United States, expressed here as the difference between difference between the average for the present day, defined here as 1986 through 2016, and the average for the first half of the last century. If you look at that figure, you'll notice that changes in temperature vary seasonally. Most of the warming has been concentrated in winter and expressed as an increase in the minimum or nighttime low temperature. And changes in temperature tend to vary here geographically as well. Most of the warming has occurred at higher latitudes, higher elevations, and been concentrated here in the western United States. That's shown on the table there on the right, where we see increases in temperature from about 1.5 to 1.7 degrees Fahrenheit for regions like the Great Northern Plains, the Southwest, the Northwest, the state of Alaska, compared to something on the order of only a half a degree Fahrenheit for the Southeast. The figure on the left here shows observed changes in precipitation, again expressed here as the difference between the average for the present day and the average for the first half of the last century. A lot of people are surprised to learn that mean annual precipitation in the U.S. has actually increased slightly by about 4%. But if you look at the figure there, you'll see that there are very important regional differences. In addition, end of the season snow water equivalent, which is simply the amount of water contained in snowpack based on snowpack depth and density, has been declining quite steadily since the late 1980s. Snowpack obviously being very important water supply for many communities here in the West. We also make projections of future climates based on global climate models and assumptions of future greenhouse gas emissions. We call those scenarios. Now, there's a whole bunch of models to choose from, a whole bunch of scenarios. They all project a warmer climate than we're experiencing here today. The figure on the left are projected changes in temperature for North America for two different points of time, mid-21st century on the top, late 21st century on the bottom, under two different emission scenarios. Here, a lower emission scenario on the left, which we refer to as RCP 4.5, which assumes that CO2 equivalent concentrations will peak in about 2040 and reach a value of about 550 parts per million by the end of this century. And on the right there, a much higher scenario, we refer to that as RCP 8.5, which assumes that CO2 concentrations will continue to increase and reach a value of about 1,250 parts per million again by the end of this century. If you look at the figure, depending on which time frame you choose, which emission scenario you look at, we're projecting further increases in temperature here from about 2 to 12 degrees Fahrenheit for large areas of the United States. The figure on the left here are projected changes in precipitation. The hatching in those figures are areas where we expect little or no change, but we are projecting further increases in precipitation at more northern latitudes and perhaps further reductions at more southern latitudes, particularly here in the Southwest during the spring, somewhere on the order perhaps of about 5 to 15%. We're also seeing and projecting changes in the frequency and severity of extreme weather events. A great example of this would be an increase in the strength of hurricanes in the Southeast, an increase in the frequency and magnitude of extreme precipitation events really throughout much of the country. On the right there is projected changes in the daily 20-year extreme precipitation, again for two different time frames under two different emission scenarios. In the interest of time, let's just focus on the very bottom right panel under high emissions for the late 21st century. Again, projecting here an increase somewhere on the order of about 20%. That has some very practical implications as shown on the figure on the left. And we'll be sharing with you here later in the webinar two different adaptation tactics to address this concern. The figure on the right here just shows some of the effects of climate change on forests. Again, here we're focusing primarily on changes in temperature, precipitation, and extreme weather events. They drive environmental change as shown in the figure, but also have implications to other stressors and disturbances that shape forest ecosystems over time. These can result in either nominal change or perhaps slow rates of change. A good example of that might be altered tree growth rates, or very rapid change. An example of that might be something like large amounts of tree mortality occurring over a relatively short period of time. both having the capacity to influence ecosystem goods and services over time. Some of those effects, perhaps positive, most of them likely to be negative, and in general, we tend to focus on the more negative effects. One of the best examples of the impacts of climate change on forests in the eastern United States are ghost forests, as depicted in this picture taken in the eastern shore of Maryland. Here, of a ghost forest, the trees in the foreground were actually killed by sea level rise and associated saltwater intrusion. Here in the West, one of the better examples of the impacts of climate change on our forests is actually expressed through our native bark beetle communities. Bark beetles are cold-blooded organisms. As you might imagine, shifts in temperature and precipitation can have direct and indirect effects on many aspects of their life histories. And in fact, when I consider bark beetle outbreaks in general, I come up with 4 grand champions. These are outbreaks of a magnitude and or extent we really hadn't seen in recorded history until very recently, most of them incited or triggered by some aspect of climate change at some scale. So the first example I have there for you today is this very large mountain pine beetle outbreak. I'm sure many of you have heard of this, really throughout most of Western North America. Greater than 27 million hectares have now been impacted. To put that into perspective, that's an area larger than our 11 smallest states, South Carolina on down combined. There, the trigger is an increase in winter temperatures have allowed in some forests, particularly high elevation forests or more northerly forests, have allowed a higher proportion of the brood to survive the winter and contribute to the next generation. And you can appreciate how that would result in population growth as long as there are still susceptible host trees on the landscape. A very similar example there for spruce beetle, this one coming from the Kenai Peninsula of south central Alaska in the 1990s. Here, the inciting factor, again, an increase in temperature, but specifically summer temperatures, have allowed that beetle to skip what we call its facultative diapause and go from a 2-year life cycle to a 1-year life cycle. And again, you can imagine the implications of that to population dynamics over time. The 2 examples on the right are a little different. They're expressed indirectly through changes in the susceptibility of host trees to bark beetles. The first example comes from the central and southern Sierra of California, where there was a very large western pine beetle outbreak. Here, the triggering factors, an increase in temperature and reduction in precipitation. And so to put that into perspective, the year 2015 was the hottest and driest on record here in California. 2014 wasn't very far behind. It was the 3rd driest and 2nd warmest. As a result, we had an abundance of drought-stressed hosts on the landscape, and western pine beetle was actually able to readily colonize those trees, resulting in the mortality of over 100 million trees. Very similarly on the right, a similar example in a very different system here involving pinyonips in our pinyon juniper forest in the southwestern United States. But again, a case where elevated temperatures and reductions in precipitation resulted in an abundance of drought-stressed hosts on the landscape, and pinyonips was able to readily colonize those trees. We're also seeing climate change influence bark beetle ranges and host expansions. The example on the left is that of mountain pine beetle here in the West. In the early 2000s, populations in interior British Columbia got large enough that the beetle actually got lifted into the active airstream and deposited on the other side of the continental divide for the first time in history. They landed in a lodgepole pine forest, lodgepole pine being one of the primary hosts of mountain pine beetle. But from there, they entered this zone of hybridization to the east involving lodgepole pine and jack pine, what we call a naive host, a host that beetle had never seen in its history. Mountain pine beetle was then documented successfully colonizing these hybrid trees and has now been documented successfully colonizing pure jack pine. The example on the right comes from the northeastern United States and involves southern pine beetle and its range expansion in New England and New York, first documented in New York on Long Island in 2014, and has expanded throughout the region since then, with the most recent and most northerly collections occurring in New Hampshire and the state of Maine. We're also seeing climate change influence wildfires in the western United States, but also to some degree in the eastern United States. Here we're observing the frequency of large fires and the annual area burned has increased, and some projections suggest that the annual area burned could increase another 2 to 6-fold compared to present. We're also seeing a substantial increase in the length of the wildfire season by up to 90 days in some areas. In fact, this actually made the national news this morning. And more recently, we're seeing an increase in the area burned at high severity. So severity just being an indication as to the amount of tree mortality in this example that occurs as a result of the fire. These variables obviously having other practical implications, like the amount of federal resources that are spent fighting and trying to suppress wildfires. That's depicted in that figure there on the right. Here in the state of California, where I'm located, 18 of the 20 largest wildfires in history have occurred since 2000, with the 5 largest occurring since 2018. We're also seeing an increase in the frequency of compound disturbances. This is when one large disturbance is followed shortly in time after another. Perhaps the best example of this is when a bark beetle outbreak causes large amounts of tree mortality, which alters fuel conditions over time. That's depicted in the figure on the left. That's a picture taken from the central and southern Sierra Nevada in the year 2020, following that western pine beetle outbreak that I mentioned earlier. And an ignition occurred, and you can see what that landscape looks like at the end of that year. That actually resulting in the Creek Fire, which became the largest single wildfire in state history, only to be replaced by the Dixie Fire the following year. We see that climate change is both directly and indirectly affecting many of the goods and services we've obtained from forest ecosystems over time. Just a few examples for your consideration on the left, things like timber production output, carbon sequestration and storage, non-timber forest products, biodiversity, cultural goods and services. On the very bottom there, air quality and human health, that's obviously related to increases in wildfire size as well as more recently severity. The picture on the figures on the right there show projected changes in winter snow water equivalent. Again, you can think of that in terms of being snowpack for 2 different points in time under that high emission scenario that we discussed earlier. Here, if you look at the bottom left of that figure, you can see that most of the snowpack in the state of California is projected to disappear by the end of this century. That having very important implications to water quality, water quantity, as well as the timing of water supply, and also affecting things like perhaps snow-based recreational services. We conduct vulnerability assessments of forest ecosystems. This is really focusing on exposure. That's simply the amount and rate of change, and the sensitivity, the degree to which species or a system is likely to be affected by that change. Recognizing that overall, the vulnerability of our forest ecosystems to climate change depends on our efforts to mitigate greenhouse gas emissions and to adapt to the effects of climate change. From here, I'll hand it over to Maria, and she'll begin by defining mitigation and adaptation for us.
Thank you very much. Yeah, so as we discussed, there are a lot of climate change impacts that we're seeing as a result of humans' emissions of greenhouse gases into the atmosphere. And so we can think about the responses that we can do, that we have to climate change as falling into 2 categories that are very closely related. And so we can think about these as 2 sides of the same coin, perhaps. One are, as Chris mentioned, mitigation actions. And so mitigation actions are those that are really focused on reducing greenhouse gas emissions that are responsible for climate change, as well as enhancing carbon sinks. A lot of these are on land through, plants photosynthesizing carbon dioxide out of the atmosphere and really taking advantage of those ecosystems' ability to pull carbon and sequester it on land. Then we also have, in terms of climate change adaptation, these are really actions that are addressing the impacts that climate change is having on humans, on natural ecosystems, and on environmental services that we're interested in. And so adaptation actions are really focused on reducing the vulnerability of systems, as was described earlier, and really minimizing or addressing those effects that we're seeing. So this presentation, for the rest, we'll be talking about adaptation options that are available and some examples of what that can look like in different places across the country. Mitigation will not be covered here, but will be covered in other presentations in this series, and is an important topic as well. And so again, just to define adaptation a little bit more, adaptation is really adjusting systems in response to climate change. These can be human systems, these can be ecosystems. And we think about adaptation actions as being intentionally designed to address climate change impacts in order to meet the goals and objectives associated with a particular place in a particular area or maybe a particular management project. And so it's that intentionality that really makes adaptation important, in that we're thinking about those climate change impacts and addressing them directly. It's really important to identify that even though talking about climate change is still a relatively new topic, it may be new in the organization or your work, or maybe you've been doing it a long time, but adaptation activities are not necessarily a departure from management that's already happening. A lot of times adaptation actions are building on principles related to sustainable management, conservation, and restoration that are underway. And again, we're putting that climate change lens on top of these activities to think about how can we do them differently or perhaps better in response to the climate change impacts that we're seeing. And so a lot of times when people are thinking about climate change, they want to know, what do we do about climate change? How do we respond? What are the adaptation actions that should be undertaken? And it's really important here to highlight that, unfortunately, if you want a single answer for how to respond to climate change, that answer is going to be, it depends. And really highlighting that there isn't a single one-size-fits-all solution to climate change, and really that those adaptation activities are going to depend on where you're working and what you're trying to achieve. We saw in the earlier part of this presentation how variable those climate change impacts are across the US. They depend on where you are in the landscape and those benefits you're looking for from the particular ecosystems or places that you're working in. And so what I'll do is present three broad options for thinking about how we can adapt to climate change. And then we'll also present some examples of what that looks like in terms of different options that are available without necessarily getting prescriptive on specific actions, since they will depend so much on context. And so the first option rather, is to resist climate change. So if we're looking at climate change impacts and we want to take an active approach, one of the options is to try to improve the defenses of the system against those anticipated changes. So how can we prevent change from happening, or maybe undo changes that are occurring on the landscape today? An example of this that can be related to climate change but isn't always related to climate change is invasive species management. We have maybe non-native species or undesirable species that are encroaching into an area, and so we undertake pulling or other practices to remove those species and resist that change. We also think about resistance as being kind of this idea of maybe building a fortress or protecting against changes that are happening, like raising seawalls or trying to otherwise prevent or minimize those changes from occurring. These are really important, but it's also important to recognize that they can be limited. And so resistance changes may not be possible in some systems, or they may have a risk of failure as conditions on the ground continue to be altered. And so this is one option that we have available in some landscapes and places. Another option that's available, and one that receives a lot of discussion, is how do we foster resilience of ecosystems of different places on the landscape in order to accommodate climate change impacts? And so the idea of resilience from an ecosystem perspective is really allowing systems to experience some amount of degree of change or disruption, but be able to return to a similar condition after disturbance. And so it's this idea of being able to bounce back, to rebound following some sort of disturbance or impact. And so we see a lot of this, and we'll hear more examples about really thinking about ways that we can introduce or reintroduce natural processes to be able to improve the health of the forest or of an ecosystem so that it has more ability to, more capacity to adapt to changes. And then another option is to be more forward thinking in terms of promoting transition and transformation in systems that are currently changing or are having a high likelihood of changing in the near future. And so with these transition and transformation approaches, we're looking to intentionally encourage change and helping ecosystems meet anticipated outcomes. And this is maybe recognizing a system is fundamentally altered or will be, and thinking about where do we go in the future in terms of these different conditions. And so again, these are broad ideas, but I think they can be very helpful for thinking about what is an approach to take in a particular time, in a particular place, recognizing that you can also mix and match these approaches in a particular landscape or over time. So coming back to this idea of it depends, what we will do for the remainder of this talk is share some examples of what adaptation looks like and responding to particular climate impacts, some ideas to put forward in terms of what this might, what the sorts of actions might be available, and then some resources to do that. I'll present two examples from the Eastern US and then turn it over to Jessica for some more from the Western US, but these are broadly applicable across the country. One of the things I really liked about the beginning of this presentation is highlighting those direct and indirect effects of climate change. And so one of the direct effects of climate change is this altered precipitation and this potential for enhanced precipitation, more extreme precipitation that leads to more frequent and severe flooding in certain landscapes. One of the places that we're seeing these impacts is in recreational areas. And so it might be that campgrounds, trails, other places are seeing more severe flooding, longer duration, and managers are thinking about how do we respond to these. We see many different approaches, but some of the examples of how these managers are responding to these impacts are doing things like converting campsites that are located in floodplains to day use areas with river access, thereby reducing, the potential for hazards associated with flooding. We can improve recreation-related infrastructure to match changing or more extreme conditions. We can do this by making some surfaces more robust, like using more riprap or using more material to be able to minimize things like erosion. But we can also introduce ways to make systems and places more flexible to accommodate changing conditions. And then we can integrate climate change into programs and interpretive signage to communicate potential hazards. And this is a big part of the really thinking about in public land management and also in working with the public of being able to also communicate how this work is happening and how changes are happening on the landscape. And then as one more example from some of our work in the East, but also relevant throughout the country and elsewhere, is thinking about how do we address extreme heat in urban areas. And this is a major climate change impact. We saw that climate change is causing warmer temperatures, and this is creating also more high temperatures and hot days, extreme heat conditions. And these conditions become even worse in urban areas, particularly those with low tree cover, because there's so much pavement and a lack of vegetation can really exacerbate, can really worsen that heat impact, which threatens urban trees and forests, but it also creates impacts to human health. And so we can reduce the human health threats by planting and increasing the amount of vegetation, forest cover in urban areas, and optimizing and diversifying the tree species selection so that way we're enhancing those long-term benefits of green spaces and of the urban forest canopy. Some examples of actions that we're seeing people take on the ground are conducting tree risk assessments to incorporate climate change so that way we can prioritize maintenance activities, focusing on tree species that are going to do better in the future, increasing urban tree cover overall, and particularly in those areas where it is going to have the most impact, planting tree species that are expected to tolerate future climate conditions and provide multiple benefits to the communities, and working with community groups to provide education and engagement in those neighborhood activities, because that's an important part of how these trees get maintained and maintained over time. And so those are a few examples. I will turn it over to Jessica to provide some more examples and some resources related to this work.
Great, thank you, Maria. So I'm going to shift to some examples for forests in the West, although they are broadly, many of the concepts are more broadly applicable. So starting with dry forests, as Chris described, we're expecting that wildfire area burned and drought are going to increase with climate change. And we want to make sure that forests will be resilient to these disturbances or have the ability to bounce back in terms of relative structure and function. So to do this, one tactic is to conduct more intensive thinning and really try to reduce the density of forests so there's less competition. You can think of that as not having as many straws in the glass taking up water. And we want to make sure that the residual trees are healthier. Prescribed fire also reduces forest density and lowers the fuel levels, and that helps to reduce the risk of high severity fire. Overall, actions that promote healthy trees will help to reduce the negative effects of climate change, since healthy trees are better able to withstand stressors like fire and drought. And then we also want to be thinking about what species are going to do well under future conditions and try to work to increase their abundance. So wildfires and insect outbreaks are likely to get larger with climate change. And so to avoid mortality across large areas, we want to try to increase diversity. So this is the idea of not putting all your eggs in one basket. If we increase the diversity of species, ages, and structures, then it's more likely that patches and trees are going to survive. And overall, resource managers probably aren't going to be able to prevent the broad scale trends in area burned with climate change, but we can decrease fire intensity and severity locally through field treatments. We also want to be thinking about where we prioritize and how we orient these treatments to make sure we're reducing risk as much as possible. So focusing specifically on drought and bark beetle outbreaks that Chris talked about, managers and landowners can take actions to try to decrease the susceptibility of dry forests to these bark beetle outbreaks. By dry forests, I'm referring to relatively low density oak and pine forests that experienced pretty frequent fire historically. So to lower severity of bark beetle outbreaks, again, we can lower forest density through thinning. And again, the idea is to reduce competition among trees so that those trees that are there are healthier and can better resist the bark beetle attack. And instead of going with stand density, we might have, based on historical conditions, you might want to think about what the future will look like with climate change and set the goals accordingly. So this might mean lowering stand density even more than we would have in the past. And then when we're reforesting sites, we want to consider what species and genotypes will be more resistant to bark beetles in the future. All right, so we often think about large disturbances as negative events because they often do have negative events on people and sometimes ecosystems. But we can also think about them as opportunities to direct the future trajectories of forests. But to be able to proactively respond to disturbance events, we really have to make sure plans are in place prior to the event so that managers aren't scrambling afterwards to try to figure out what to do. And when post-fire planting is desirable, managers may want to consider changes from current practices. An example, you might want to consider lowering stocking density and trying to increase heterogeneity of planting overall to try to increase resilience to fire and drought. We might want to consider different genetic stock that has been used in the past to try to increase seedling survival. And then land managers and owners can try different techniques in different locations and think about it as an experiment to see what actions will be most successful in the future. So with increased disturbance and species moving in response to climate change, there are going to be more opportunities for invasive species to establish. And so we need to be more vigilant with regards to invasive species to help reduce their spread. And a current strategy is called early detection and rapid response. And this strategy is going to continue to be important in the future with climate change. We can think about controlling invasive species with a variety of methods that can include biological controls, herbicides, mechanical treatments, and really making those decisions about which controls to use based on the ecosystem, the species, and the degree of invasion. And it's also important to make sure native species are competitive and promoted in restoration activities. So future climate, again, can be a consideration in choosing the species to include in seed mixes. Okay, so Maria talked about the increased risk of flooding with climate change and how that will affect recreation sites. And increased flooding is also going to affect other built infrastructure, including roads, bridges, and culverts. And so to address increased flood risk, a general adaptation strategy is to try to design infrastructure to be more resistant to these higher stream flows. And so that can be done in a number of ways. One is to install larger culverts to allow higher stream flows, and we can also try to remove roads from floodplains, those roads that are likely to be hit over and over again with flooding impacts. And as Maria mentioned, we also might want to think about the location of some of our campgrounds. People like to be camping near water, but those sites are going to be at increased risk of flooding in the future. So we have increased temperatures and changes in stream flow are also going to affect some of our special habitats, like wetlands and riparian areas or the vegetation along streams. And so droughts and disturbances like fires and floodings are going to affect riparian vegetation and also the adjacent aquatic ecosystems. If we have lower water levels with drought in the summer, the water-loving species that typically grow in riparian areas might not be as competitive. So we might want to promote more drought-tolerant plant species. We have to think about existing stressors and trying to reduce those so the systems are better able to be resilient to climate changes. So in riparian areas, that can include invasive species, intensive grazing or browsing. And then overall, we want to protect these ecosystems from effects of intensive recreation and other human uses because they're going to be really critical in keeping stream temperatures down and ensuring we continue to have clean water. Okay, shifting to aquatic habitat, a primary effect of climate change on aquatic ecosystems is increased stream temperatures. And these are going to be stressful to our cold water adapted species like salmon. So a general strategy to address higher stream temperatures is to keep as much cold water habitat as possible. So we want to conduct restoration where needed and to try to maintain this habitat where it currently exists. And then where habitat is degraded, restoration can help to increase habitat quality. So this could include actions like reconnecting floodplains, restoring side channels, promoting large wood, and again, making sure we have intact riparian vegetation to provide shade and keep the stream temperatures down. So I want to provide one final example for recreation, and particularly for winter recreation. So we know that increased temperatures overall are really going to have negative effects on snowpack and winter recreation in a lot of locations. And from the perspective of a management agency like the Forest Service, it's going to be important to be flexible in the management of winter recreation. And we know that use is likely to increase in places that still have snow. And so facilities could be expanded in those locations. We might also want to think about diversifying options for snow-based recreation in those places. So for example, sledding or tubing to help make sure that people continue to have those recreation options. So we've just presented a wide variety of adaptation options to consider. They're not all appropriate in all locations. Like Maria said, it does depend. You likely won't have to worry about all of them, which is good news. But it's really important to evaluate local conditions and use knowledge of local systems, think about objectives for particular sites, and see what the effects of climate change have been to really decide on specific tactics to implement on the ground. It's also going to be really critical to work with partners, adjacent landowners and managers, tribes, non-governmental organizations to implement these adaptation actions across large landscapes. And this will help to ensure that our adaptation actions are effective and we reduce the negative effects of climate change as much as possible. Right, and to close, we wanted to make you aware of two key resources related to climate change vulnerability assessments and adaptation in forests. And so the first is a story map that has links to all of the climate change vulnerability assessments that have been conducted for national forests and adjacent lands. And this is a great resource to find information on climate change vulnerabilities for a particular area you might be interested in. So the URL is on the screen, and I'll also put that in the chat. And then finally, to get some ideas for adaptation, there's a national level compendium of climate change adaptation actions. And so this is a searchable online database, has a user-friendly interface. You can search by resource area, region, climate change effect, and other keywords. It also includes peer-reviewed citations for different adaptation approaches and as well as implementation examples. And this is on the Forest Service Climate Change Resource Center. The URL is there on the screen. And again, I'll put that in the chat. And so with that, we thank you for joining today.
Thank you so much, each of you. This was just a very useful overview of this topic. We'd like to thank you for the thought you've really clearly put into choosing just how to introduce these topics today. I want to very much thank all of today's speakers. This was a very informative webinar, and thanks also to today's participants. Your engagement and interest in knowing more has just really driven this effort from the beginning. So thank you for being here. A recording of today's presentation will be available on USDA's YouTube site soon, so look forward to that, as will the PDF version of the slides. A recording of April's webinar is available online. See the chat for that URL. I also want to invite you to next month's seminar on June 9th by Dr. Shakaby Wilson from the University of Maryland and Dr. Frank Lake from the USDA Forest Service. Dr. Wilson and Lake will be discussing climate justice, an important issue. It should be really an excellent discussion. So we hope to see you again on June 9th. Thanks again to our speakers, and thank you very much for your participation and your excellent questions. Enjoy the rest of the day.